Hello, everyone. Welcome to this week's binary episode of the Day Zero podcast. For those who didn't tune into the bounty episode for this week's episodes are being recorded and not live streamed due to some stuff going on my end. Next week's podcast will also likely be canceled. Hopefully, things will be back to normal the week after that, but I'm not 100% sure yet. And because we're recording this week, there's no spot the ball to jump into, so we can get right into our topics. So, up first, out of Google, we got news that Google is expanding their research reward program from kCTF or kernel CTF, which has been around for a while, to include a few more programs. And I'll let Z get into this one.
Yeah, and if you're not familiar with kCTF, one of the main things about that is just the fact that, yeah, you can still report like O-day vulnerabilities and such, but you would also get a bounty for writing end-day exploits and just capturing the flag on their kCTF environment. And so that meant you could take end days and you would get bonuses for like having unique or like not otherwise seen exploitation strategies. So they've taken that idea from the kCTF and gotten a lot of information more on the exploitation side of things, taking that and now they're applying it into V8 and KVM, with the V8 CTF and KVM CTF coming up after that. Which I thought was just neat. It's maybe a little bit of motivation to get some practice doing the exploit dev and kind of get in there with that. From kCTF, they've also published this kCTF cookbook, which gets into like the exploitation strategies and kind of tries to boil them down to like some key components and just like a really useful, if you're doing Linux kernel exploitation, a really useful reference for how people have done some exploits. Um, so I'm excited to
Useful to pull
see.
inspiration from, for sure.
Yeah, and I'm excited to see the expansion. Like, I do think it is a very beneficial program. So seeing the expansion to V8 and into, I guess more so V8 is obviously a lot of people are interested in doing browser exploitation. It's never really been like my major focus at any point, but a lot of people do care about it. So I think it's nice that they're expanding into that. 'Cause a lot fewer people kind of care about Linux kernel exploitation, although Android obviously has some demand there.
Just to clarify, V8 is Chrome for those who aren't aware. It's the Chrome JavaScript engine. Um, So yeah, V8 the V8 CTF was launched for Chrome, KVM CTF for kernel-based virtual machine. I did look into some of the particulars. They link off to the rules. So V8 CTF has a reward up to 10k, and they expect a reliability of at least 80% and a time to exploit of less than 5 minutes, which is pretty generous. And similar to kCTF, like Z mentioned, you can use end days as well as 0 days if they manage to get you the flag. The KVM payouts are higher and more tiered, so a full VM escape would net about 100k maximum. Arbitrary write would be 35k max, arbitrary read at 25k, and a host DOS of 15k. And those don't stack. It's whatever is the highest primitive you're able to achieve. I do find it interesting that the V8 CTF reward was as low as it was. I was expecting it to be a bit higher because like the browser market is not that much lower. I wouldn't think than like the VM escape, like KVM. So I don't know. I thought that was a little bit weird, but because like a V8 exploit is, especially using a novel technique, is going to be quite a lot of work. But maybe that'll end up going up in the future. Who knows?
So I don't know for sure. I didn't look too deeply at this, but my guess would in part be because the V8 CTF is probably focused just on V8. So you don't have all of that surrounding Chrome sandbox and everything. It's just getting the code execution within the V8 environment. Whereas the
That's fair.
KVM escape, um, I was kind of think like obviously KVM escape is a full escape from the KVM, which despite the name, like it's not a full
Basically, the V8
VM, but
attack surface is a little bit like you have more to work with.
yeah, like for getting to the host, you have a bit more access there, but it is very heavily used. You know, Kubernetes uses KVM, and obviously a ton of companies are using that. Google themselves are using that. So while the demand, like client side demand, obviously V8 is going to be a lot more hit. Well, KVM definitely has like a very wide usage and is just kind of overlooked as even being part of those stacks because there are other things that kind of take the focus. But yeah, if I had to make a guess there, it's more just because the V8 escape is only still keeping you inside of V8. It's not doing the rest of the Chrome chain. But that is kind of just a guess on how they came up with the values.
Yeah, and I guess that's fair. But I did want to point out what the reward values were and that the rules were up, so that if you had to choose between a program, the information is all there for you. Even though the KVM CTF, I don't think that's launched yet. I think it's only the V8 CTF that's launched so far. They stated that the KVM one is going to launch later in the year, so hopefully within the next month or two or whatever. Well, I
Yeah, they
guess
just say
if it's in the year, it would
upcoming.
have to be. Yeah.
Oh yeah, I wasn't even thinking about the fact that we're close to the end of this year. I was just saying, yeah, anytime within the next 12 months.
Yeah, no, we're pretty close. So yeah, speaking of some bugs that can have some wide impact, our first full exploit post is the infamous WebP 0day that was patched in September and written up by Ben Hawks. Quite a complicated bug, probably one of the more complicated ones that we'll have covered because it deals with the particulars of Huffman coding, which I don't really have experience with. I haven't really tried to write image parsers or anything like that, but Z dug into it and went through the pain, so I'll let him talk about it here.
Yeah, and Huffman coding kind of underpins a lot of modern compression in general. Like it's definitely more than just images. Like it started with text, and the first Huffman tree was really just about compressing text down, largely because images people were still using like lossy compression, or you're still okay with that. Anyway, like as a bug, it's really hard to kind of craft the input that hits this one. Um, and there are probably some details that I'm not exactly understanding. I think I have kind of a grasp over this, but I definitely still have some questions. So I'm kind of going to apologize up front if I maybe mislead a little bit on this one. So within WebP, if you're not familiar, WebP is an image format, lossless
A very
compression,
annoying image
and
format. Yep.
yeah, and this is within uh VP8L encoding or compression system. They've got the decompression code here. Um and it's this decompression code that actually creates the issue. But underlying all of that is they're using Huffman codes, and so that would be used, of course, for the pixel data being encoded with these Huffman codes. And then not just that, but they take the Huffman codes, and those are also encoded with Huffman codes because you want to compress the table of the Huffman codes for the image, so you're sending less data too. So, they kind of have these layers of Huffman codes. So part of the process here is
We
they
heard
have
you
to
like Huffman
build.
codes. Yeah.
So they have to build the Huffman table back up or while they're processing the data in the actual image file. So this is attacker controlled data that's being processed, and they'll build back up the Huffman table. One thing that kind of confused me a little bit here is they refer to as build Huffman table, but in reality, it seems like they're building at least in this case for what they found is exploitable was 5 Huffman tables, and internally the WebP structure is they have a Huffman table structure. That table contains Huffman segments, which then contain Huffman codes. And what it seems like is effectively every segment is like just your Huffman table. And if you're unfamiliar, the core idea with the Huffman table is you have some. Actually, I should say the core idea is starting with the Huffman tree, which is usually the more understandable way of doing this, where basically if you turn a bit on, you go left or right, or okay, if you turn a bit off, so it's 0, you're going left. If you're turning the bit on, you're going right, and you kind of use that sort of table structure to encode bit sequences that map to character or like byte sequences. And effectively, what you're getting is a mapping of bits to bytes that it decompresses, and there's a whole frequency thing for like how to actually encode that with your data. It's customized to whatever's actually being compressed, where the most frequent data gets encoded with the fewest number of bits. um, and they have a little bit of a strategy for choosing those bits, so it's able to decode without making any mistakes, so you won't have a case of bit sequence that could be read in multiple different ways. Like every bit sequence is, of course, it's unique for what maps out to bits, but they're also not ambiguous, so not all possible bit sequences are used. Like, if you use the bit 0 for one or for one set of bytes, and then you use let's say 0, 1 for another set of, or as bits for another set of bytes, when you're parsing that, you're going to encounter that 0, and how do you know there's the 1 coming up? You kind of have that ambiguity when you just kind of reach that first 0. Is it going to be the 0, or should it be parsed as the 0, 1? So they kind of craft the bits in such a way that you don't have those ambiguities. As you're reading it, the first time you actually hit a match with the bits that you've read will be the character to put in that place. That kind of matters, but I guess I'll get on that a little bit later. But that's kind of your Huffman tables are being built up here. They talk about having to build 5 segments up for where they found the vulnerability. I'm not sure if that is something that's coming from the WebP structure where you encode like these 5 different things, and that's why it's always 5 segments, or if there are cases where there will be more segments. I can't say that the case that they found to be vulnerable, they were having to craft 5 segments. Unfortunately, I am not that familiar with the internals to actually know, but the core issue here is somewhat simple to understand. In that, what they do is when they're building the Huffman table, they of course allocate the space for the table. And what they do is they basically take the color cache bits, like how many bits being used for that, and they just have a lookup table pre-computed over how big all of these Huffman tables can be. So they have the table sizes effectively predetermined. I do also have a link to the patch commit here, which does help when you're looking at some of this code to kind of see what they're doing or what seems a little bit weird. I think they have the allocation in here too. Yeah. So this Huffman table, what's doing is this table size value is what's fixed. That is coming just out of a lookup table where they pre-computed, for this many bits, or the color bit thing, for this value, you're getting this size. And that just has to do, I believe, as I mentioned, where there's kind of that certain bit sequence that it's using as its encoding data, as the Huffman tree's encoding data. The table size, I believe, is just because you can only go so far in a legitimate Huffman table. Like there's only so many bit sequences you could use for a 15-bit series or whatever. There's only so many sequences, so it can only be so large. And so they're just allocating for the largest maximum size. And then the core problem or the vulnerability ends up being, well, what if you create tables that do encode bigger than that? Fortunately, they do somewhat defend against this, because I'm just trying to find my link to the commit for this one. I believe this is it. Yeah, so right here, as they're building the Huffman tree, so this is the building the Huffman table. I am going to use those two terms interchangeably. They are building a table, even if I say tree, because that's kind of mentally what I've always worked with and kind of know better. They're building a table, which is that whole tree system, but instead of that, it's just a table hash map. Well, I don't know exactly what the internal is here, but it's a table for them to do lookups of the bit sequences instead of needing to walk the tree. Anyway, in this build Huffman table, towards the end here, they have this check, and this is basically like a consistency check, a sanity check, making sure the number of nodes that were generated are actually what they calculated as should be the max, or the number of nodes, and if that fails, they just return a failure. They return that they create 0 nodes instead of the actual size that was created. So in one sense, you can't craft an invalid table because that check's going to fail. Problem is that this thing, while it's building the tree, it's doing the writes in this. Like it is writing to that buffer. So if you do get going out of bounds and creating too many nodes, then it's just going right out of bounds, and you'll enter the error path after it goes here, but you've already done the write up in the earlier code. And so effectively what ends up happening for this vulnerability is They craft 4 legitimate segments that are as large as possible. They're trying to get themselves into the buffer as far as they can. So they are all maximum size, but completely legitimate, so they don't end early. But on that 5th segment, when they're creating that, they create a malformed segment, and they have kind of an image of it. So the image I've got up on stream right now, or I guess on recording right now, kind of shows the Huffman table where they'll have kind of at all of these terminal nodes, they'll have a double circle just representing basically that they've got an actual value there. And this is kind of what the normal tree-ish could look like. All those terminal nodes are ending with a value, and you can kind of see, I don't think this will show up too well on stream for you guys, but you can see like the 1 and 0 path where going left gives you 1, right gives you 0. I think I said the opposite earlier, but it's really just a convention on that. Just how you kind of follow the bits, and then you get down to whatever value's been encoded there. So that's what a normal one should look like. Everything, as you get to the end, the terminal nodes, they've always got values down there. And then you've got their malformed one that was able to trigger out of bounds right. And that one, you'll notice it looks fairly similar at the start. This early part looks fairly similar. If you look closely, you can kind of see all the double circles, which indicate they're valid nodes. Kind of get there, and the rest of this is a bunch of nodes, and all of these terminal nodes, I'll zoom in slightly for you guys, but all of these basically just terminate. They don't have values, and they're nodes that would never be reachable normally. Like if you actually took the bit encoding, these are where you're getting into like those ambiguous bit encodings, things that just wouldn't work normally. But they're creating a whole bunch of extra nodes here, and each node is getting its new table entry, so it is writing out of bounds and writing somewhat attacker controlled information from this out of bounds as it's writing, because it's creating too many nodes. They're not actually bounds checking as they write, they just assume you're going to fit. So yeah, fundamentally, like that core issue is just the fact that it allocates based on the fixed size, doesn't actually validate that's going to fit within there, and it's writing, and it doesn't detect the issue has happened until after it's already done these out of bounds right. So in a sense, it's kind of easy to explain, but also very complicated to understand the layers of the Huffman trees here, the Huffman table and the segments and all of that. Getting really complicated to hit it, but fundamentally, I would say like a big part of that error is just that consistency check happening too late. And in fact, the patch is basically, if it fails an earlier check, they're just not even going to bother decoding it. They're just going to kick it out and error early with it. So they don't really go into how to exploit this. He does mention that he did manage to get up to like a 400 byte out of bounds, right? On Twitter, there was kind of a question raised by someone they somewhat collaborated on this with, Misty Mountain Cop. I'll just bring up this tweet here. Mentioning astute observers may notice a problem with their sample. The 5th invalid Huffman table causes the WebP decoder to take the error code path, effectively ending decoding. Seems problematic for zero-click exploit. So as mentioned, this vulnerability was seen in the wild, but as far as I know, Ben Hawks, author of the post, didn't have access to an actual payload or an actual attempt to exploit this, but went about just trying to figure it out from the commit. From the problem that was reported by Apple and the public commit that came following that.
So that's something I think we skipped over, but I do want to quickly mention is they're not 100% sure that this bug was used in the BlastPass chain, but they're reasonably confident. But yeah, Apple did, like the patch commit that Z referenced earlier, Apple reported this to Chrome after they were made aware of it being exploited in the wild. So that's kind of how the information got to Google to patch it. Which is why like a lot of things that parse WebP are suspected to be vulnerable. It's not just Apple devices, Android devices are also likely vulnerable, as well as a whole host of other things. But yeah, I think we did kind of skip over that, so I did just want to quickly shout that out. And that's
Yeah, I
also
was
why
going to
there's
get
not
into it
really any
now.
exploit information. Yeah.
Oh, yeah, I was going to kind of jump into that now as like, so this is Ben Hawk's take on how how this vulnerability could have been exploited. It's believed that this is the same as the blast pass vulnerability reported by Citizen Guard. I think I always want to
Citizen
think
Lab.
Citizen Lab. Yes, I I always want to go to Citizen Zero, which I think was like Snowden movie or something. I haven't even seen it, but I've got Citizen Zero stuck in my head. Every time I try and remember the name of this company, I'm like, no, it's definitely not Zero, but what is it? And I can never remember. We talked about this like right before the podcast.
Yeah,
Inspector
that's
said
why I was
Citizen
laughing
Lab,
for.
and I still
Yeah.
screwed it up. I can't remember for the life of me. But yeah, they report on that. Um, one kind of interesting just about that was just the fact that it was called Blast Pass because iMessage has their Blast Door sandbox. And by, I guess, using this image exploit in a passkit attachment, they would just bypass the whole iMessage sandbox altogether. Um, Not really relevant to this vulnerability, but I thought that was kind of an interesting aspect too, just dodging the sandbox through how they're getting their image actually, or through what they're getting their image loaded through. But yeah, on exploitation, we don't have like a sampler to see how like it was actually exploited in the wild. I think
Which does
it's
kind of suck because when I'm reading through this, the bug is cool. Don't get me wrong; like it's a very deep vulnerability that, like, I'm not surprised it's escape notice for this long. Like, this is a really technical bug. How you would actually exploit this, though, especially in the failure case, uh, it's hard to imagine how you would, like, you're not in a great position as an attacker, I guess, at the time you'd be exploiting this bug. Like, you're dealing with a message app. You typically don't have like a lot of like primitives or control over the heap state, and this ultimately is like a heap overflow. So I would be really interested in how you would reliably be able to exploit a bug like this. It seems like a really tight exploit scenario, but
yeah, and this
we
is
just
one
don't
shot
have
too because it's
that.
just an
Yeah,
image coming in,
exactly.
which is especially challenging for kind of the reasons you said. You don't have the allocation control and stuff like that. Yeah, so they had mentioned like they were able to get like a 400 or up to 400 byte out of bounds write, which is fair. That is a very significant amount of data to be overwriting. Um, in the air path, so the writes have already happened before it goes down the air path. So you do have this window where these writes have happened. Yes, it airs, but they have happened. You do potentially have other data that isn't even necessarily WebP related sitting around in the heap that you might be next to. Don't have a lot of grooming control unless they have something crazy going on, which has been seen on iOS exploits before. I'm thinking of the one where they had what was it? They used like a decoding library were able to create basically like a Turing complete set of gadgets for themselves to actually get something out of it, but that as far as I'm aware, that is not the normal case. Because yeah, with like such a large out of bound right, like it feels like it should be exploitable if you have the right knowledge, and getting that right knowledge is going to be a challenge. They do not go into exploitation. We don't know, but I don't know. It obviously it is exploitable. Like they did manage to do it somehow. Maybe they had some other way of triggering it though, or like something else go on with it. Can build better primitives.
It's possible they just were able to find themselves in a more favorable scenario than what this exploit strategy led to.
Yeah.
Because this is what, Ben Hawks had thought up, not necessarily what the attackers used. So it could just be something like that. But I kind of want to, like, keeping all that information in mind, there was a lot of, I guess, fear mongering around this bug. So I was looking around on social media and stuff, and there were people like, "Oh, WebP, this is terrible. Like, it's supported everywhere. This could be used to pop anybody in like every device." And I don't want to completely hand wave away the concerns. Like, even towards the conclusion of the post, Ben Hawks talks about how, this bug likely exists in a lot of products and whatnot. But actually trying to weaponize this bug would be like a serious endeavor. It's not like you're just going to see exploits popping up for this everywhere used in malware or something. Like, it's a technological achievement weaponizing a vulnerability like this, especially in like the mobile case, like Android and Apple devices with sandboxing and such. So, I did want to bring that up and just say that I think there is a little bit of hyperbole going around with this vulnerability. Um,
Yeah, and I'd
and
agree. Like that is, I think, a really important point. Is a lot of people kind of talk this bug up, and for those that found it who have a good understanding of exploiting it, they very well may be able to continue to use this or port it over somewhere else. They depending on how they, what their strategy look like. But I think, as far as I'm aware, I'm just looking it up right now. Like, there hasn't even been anybody that has managed to weaponize this into a proof of concept. I don't think there has been any proof of concept published yet. So,
not that I've seen.
like, it hasn't been that long. This was disclosed, or this was posted, I guess, on the 21st. Uh, the vulnerability itself was kind of disclosed and known about before that. Uh, yeah, giving it the few weeks. Fact that like everybody had eyes on this, knew about it, and nobody's actually managed to get a repro going, that does something useful. Does speak, I think, quite a bit to the difficulty of actually trying to exploit this somewhere. Um,
Yeah.
Especially
Yeah.
because, like I said, it is prevalent. Like, it's not like libwebp was this unknown library.
Yeah, I think they mentioned like it's been like picked over and it's been fuzzed and whatnot. Like, it's not just some obscure area that has escaped notice. Um, Now, something else I wanted to bring up too that is talked a little bit about in the conclusion. It's kind of along the same line of thought, but they talk about how I'll just kind of read out this quote at face value. So, the lack of available technical information from the vendors here made verification challenging, and it's questionable who this really benefits. And basically, what they're talking about here is the fact that attackers, they're always going to be more motivated. They're always going to have more, readily accessible information, and be willing to dig to get that information. And like, this lack of documentation or technical information by the vendors, like, it seems like they do it in the interest of like, hey, if we don't make information available, then people won't want to put in the effort to attack it, which is just proven wrong time and time again. And Ben Hawks is kind of making a case, like, an additional data point in the case that it's like, situations like this only really benefit the attackers because defenders are not going to have, typically they're not going to have the resources to look into all the particulars of this bug, and if they need to be, if they need it patched, or if they have to come up with a patch themselves, how to do that. Like, it's very stacked in the attacker's favor, being so vague and providing a lack of technical information, which I don't think we talk about too much on the show, but
It does come up
it's
a
it's a
little
valid
bit.
concern, I think.
Yeah, it's definitely something like I've talked about a fair bit, not necessarily on the podcast, but just in general, because it ties in to the wider discussion that especially some newcomers will have is why even do a vulnerability disclosure at all? Doesn't that just advantage script kiddies? And what it actually does is it brings everybody up to the same level. It takes away the advantage that attackers have by giving, the security professionals who aren't going to be able to invest that same amount of time. It brings everybody up to the same level. So yes, it does also bring script kiddies up, but it brings everybody else up to the same level as those motivated attackers.
It
Um,
raises the floor, yeah.
yeah, yeah, that's a great way of putting it. It raises the floor when we put all the information out there, and I think that is better overall for everybody's security. Is to have everybody at that same starting place rather than rewarding people for uh being well, obviously they're going to get their reward, like monetary reward or whatever they're doing. Like, there's going to be that motivation, but not giving an advantage to those motivate people, but actually advantaging the defenders. Yeah, I think it's a really important point that it really doesn't, like, the only thing it really saves is uh reputation, corporate reputation from the
Yeah.
vendors, and being able to downplay things and just not make it clear. Also talk a little bit about the aspect of fuzzing and how this would be a hard bug to fuzz unless you happen to have your bug fuzzing in just that right area and already kind of targeted towards this sort of issue. Because it does require that like 4 of your 5 Huffman tables be, or segments, be valid, and then just that one invalid one that's invalid in just the right way to create an issue, and so it doesn't fail somewhere earlier or something. uh it is, I think, a fair point that there is a lot of trust in fuzzers and using fuzzing for security, and it's not a
Especially for things
replacement.
like images, like file formats. It's a huge thing, especially.
Yeah, I'm not sure if it's necessarily an over reliance on it. um it definitely gets the priority, but it does to some extent work. Like, I guess kind of what I've got in my head is isn't necessarily an over reliance or just a lack of doing other things. Like, I don't think it's that we should step away from fuzzing and like fuzzing doesn't work, because fuzzing does work. As I've said a few times, like, it is unreasonably effective, but it's not the only thing that should be done. But for many companies, for a lot of things, like, it is a very good step and should be part of the process, but so should the manual auditing, so should the code review, and especially paid third-party audits. As important as the code reviews are by like an internal team checking all the commits, third parties coming in, a different set of eyes, different set of assumptions, can bring up issues that get overlooked by the internal team. And the internal team, though, does have better insight on certain issues that are very kind of localized and internal to that team. And they have some advantage in a way, but third parties do bring in an advantage too. Like, both of those need to be there as part of the overall process on security. It's not just fuzzing.
Yeah, you need to have like basically what he's calling out for here is the hybrid approach. So investing more into the proactive source review and not dropping fuzzing or anything, just incorporating the source review as well.
Yeah, the second point, so he does make the 2 point thing. There needs to be bigger investment in proactive source code reviews and renewed focus on ensuring parsers are adequately sandboxed. Sandboxing aspect, Google's done a pretty good job of this, like, especially since Stage Fright. They've done a really good job of kind of targeting or getting in on Android and locking down the attack surface, creating sandboxes for a lot of things, moving things into sandboxes. Think those steps. I think a lot of companies overlook that aspect of just trying to sandbox segments of their code, and that's not always possible depending on how it's running and stuff. But attack surface, limiting the potential attack surface is huge just in overall security. Um, if vulnerable code can't be reached in a vulnerable way, it's not exploitable. So I just wanted to call out that I think that is also a excellent point.
All right. So early on in the show, we talked about kCTF, and our next post dives into that a little bit. So this was a post over the summer. It's a Linux kernel exploit write-up from Hombre on a bug that ultimately came out of a kCTF report, another IOU ring bug. Just to be
Yeah,
clear,
and
since then, IOU ring has been disabled on the kernel CTF config, but at the time it was reported it was still a valid target.
can I
Sorry, what was
just
that? Zane?
say, like, I'm super happy to see a post from Hombre, because I think like last time he posted was probably a year ago, and that was just a CTF thing. And then it wasn't until like 2021. I mean, he always has really great posts, and this one's no exception to that. So I just want to shout that out.
Yeah. So like I said, IOU ring has been disabled on the kernel CTF config because it was just I think at one point literally every single bug that was reported to kCTF was an IOU ring. So yeah, that's that's changed since this bug was reported. But yeah, so they saw this bug reported on the kCTF spreadsheet and was curious to dig into it and see if they could exploit it using techniques that weren't super well known or published. The original vulnerability was actually pretty simple. Basically, when processing these IO ring op message ring commands, um, operations for signaling another ring. That would take a file descriptor for the ring or file to signal, and then after it finished processing, it would just do a put or ref count decrement on the file. But the problem is, if that passed in file was what's called a fixed file, which is like managed by IOU ring, that file would already get its reference count decremented by IOU ring unregistered files. So in the case of fixed files, it would get freed while the file descriptor was still valid and installed in the process. So classic UAF, very nice bug having like a file descriptor to a freed file. Like that's the type of primitive that you would go for from a weaker bug. So it's definitely a nice thing to start off with. And the rest of the post goes into exploitation, which is a nice read as it's more of like a journalistic style approach of trying to do some novel Linux kernel exploitation, trying to see which routes worked and which ones were like had some problems. So first thing they did was try to get an arbitrary read primitive, which is kind of where my mind goes a lot of the time. So they started looking at syscalls that would take a file descriptor of which they would have a freed file for and do a copy to user using a pointer that was stored in the file. They don't say exactly how they do that, but I'm guessing it was just cross references. But there are some other tools that could be used for that too.
Yeah, I guess they do mention actually that they use cross references to visit the kernel code base, which handle the syscall implementation, just Control F copy to user.
Yeah, so there you
Um,
go.
so yeah,
This is fairly straightforward cross referencing.
yeah, and
So
I'll shout out because we did have a question out of Discord a little while back. I forget exactly who asked it, but it was basically about how somebody would look for primitives for a kernel exploit. They end up talking about a double free, but use after free is kind of related to that. You just only have a little bit less control. Um, and honestly, that sort of thing, like just reading the code, is completely valid. I like to jump into CodeQL. I think unsurprisingly to a lot of people, given how much I'll talk about CodeQL, I kind of like that because you can kind of map in or write queries that match your constraints, but there's also like PA hole and stuff too that can be used to find the right things, but you always have to, or it always ends with reading the code to actually figure out how to hit the path that does whatever you want, or how's that structure used and such.
yeah, so in this case, they managed to find a pretty good arbitrary read primitive quickly through the fget read write hint file control operation, which would take a file inode's write hint pointer and copy out from that. Um, from past write-ups and inspiration, they basically decided to use pipe buffers for overlapping with file data. So in the Linux kernel, like file objects are going to be in their own cache, and pipe buffers are also going to be in their own cache. But if you free a whole page from a cache, you can get that reclaimed by another cache. And pipe buffers in particular are pretty useful because you can control. Well, for one thing, you get a whole page of them, so uh, you have less randomness or noise in your allocation, and then also you can control like the entire contents as an attacker, so it's a very useful primitive. So yeah, by overwriting the file object with contents control to the pipe buffer, they could overwrite that pointer that was used for the file hint, and yeah, they had arbitrary read. It was pretty easy. The next question, though, is, what do you do with it? Because you haven't defeated kernel ASLR yet. You can read a pointer, but where do you read? Well, what they decided to go for with that is something that I think I'd seen before, but I'd kind of forgotten about, which is CPU entry area objects. These are objects that are at like a fixed address, and they contain per CPU information for things like interrupt handling. And so by using this arbitrary read and just reading that fixed address, they could read out the error entry function pointer and defeat KSLR pretty easily. Where it got a bit trickier for exploitation was getting an arbitrary write. Using the same trick of searching for copy from users on the file didn't yield results the same way right away, though what did end up turning results was looking for copies on the private data of the file. which for those who aren't familiar with the Linux kernel, every file has like a private data field. It may or may not be used depending on the driver that's implementing, the functionality using the private data. Typically, it'll be used by like the read-write handlers or ioctl handler or whatever. So it's an opaque pointer. How it's used is depending on whatever subsystem is setting it up. And it turns out a good place to hit was the IOU ring system itself, specifically IO message ring, where the bug is. So the target context pointer that's used by IO message ring is ultimately casted off from the private data field. And even better, eventually this IO commit CQ ring function for committing a write of the completion queue ring would use that context for writing the cache completion queue ring tail to the CQ tail pointer, which is attacker controllable. So ultimately, that gets you an arbitrary write of 4 bytes. You have arbitrary read-write primitive, and from there, it's fairly standard. They use the arbitrary read to find the task struct of a child process, and then use the arbitrary write to smash the task struct to privilege escalate. So fairly standard exploitation on the arbitrary read-write side.
Yeah,
Though there were some neat tricks to get there, like the CPU entry area.
they also use the read to find the test struct for init. So they use their child structure and overrode with information from init. And
Yeah,
that was so, especially with like the NS proxy and all of the pointers in there, they would have kind of the legitimate thing that isn't going through the namespace proxy to replace their own struct with. So, I
yeah.
mean, effectively the same strategy, just that's also where they got the data to copy into their own structure from.
Yeah, so fairly standard on that side, but there were some cool tricks to get there, and that's not too surprising because one of the goals that Hombre had set for themselves was uh trying to find a less well known or documented techniques. So yeah, they came up with a pretty cool chain here. Not sure how reliable and whatnot it is, but given the circumstances and the fact that they were doing the cross cache, uh, it's probably fairly reliable. So
Yeah, I mean, it seems like with the pipe buffers, since you can read and write on them, like you should be able to do a pretty decent job of figuring out like where you are when with everything. So I don't know, I feel like it could be reasonably stable for an exploit. They don't actually mention, but nothing really stands out as being like really unstable to me.
yeah, I agree. So
Um,
getting into our next post, unless you had
so
something you wanted to add there, Z.
yeah, I was going to add on here just kind of a shout out with this post. What they're kind of doing is just, something I think if you're trying to learn exploit development, trying to go through and do this same sort of process where it's like, yes, existing strategies and techniques exist for what you're trying to do, but trying to come up with your own, even if they're variants on it, taking the time to actually hunt and search for your own primitives, I think is a really important skill to actually practice, especially as you're getting started, learning things, because there's no real way, like, at least I've never seen like a course that really teaches you to hunt for primitives or like the possible users and all of that. So just taking the time and kind of putting yourself in the position to practice that sort of skill, I think is rather valued. It's something I call out in like that CTF to real world post I did. Is it already a couple years ago? I'm not sure. Maybe
I believe
just a year and
so.
a
Yeah.
half. Um, but did that quite a while ago. I kind of call out taking the time to actually practice hunting for your own strategies, and it's kind of what they're going at here. And I appreciate kind of the details we included, a little bit about how they hunted, but just the fact that, like, yeah, there was a similar one that they took inspiration from, and reading all of that. I just appreciate those details out of this post.
Yeah, and even if you're not, or sorry, even if you're an experienced exploit developer or whatever, it's good practice for ramping up on a target too. So it can get you, it can force you to get familiar with the internals of whatever target you're looking at. So
Yeah, like the
I think it's
way
good practice.
when ramping up on a target, the way I'd kind of approach it is starting off by learning what the common techniques are in the first place and just implementing them that way. And once you kind of know what's common or not, then going into your own. Because, yeah, going into your own does force you to explore a lot more code than just trying to follow the common ones. But it's always useful to know what's actually being done and what actually works right now.
So, getting into our next post, last week a buffer overflow was reported named Looney Tables in GNU libc's dynamic loader. I'll let Z get into this one.
Yeah, and this one's fun. I mean, something C is known for, string processing issues. We've got our glibc tunables. I'm going to be honest, I don't entirely understand what exactly you're doing with these. I think I've run into them exactly once. I don't think I ever need to use them. I just reading docs came across them. I think it's something like that. But glibc basically started a program. You could have this glibc underscore tunables environment, and then when the glibc loader is going through, it's going to process these tunables in order to get its, I guess, sort of runtime config. I'm just trying to find.
It allows you to configure various settings of the runtime. So, you can set the x86 shared cache size or
Yeah, I
the
thought
T
I had a
cache count for
link to it.
malloc or something like that.
There we go. I thought I had a link ready to go with the tunables, or at least some list of them here. Uh, yeah, this is from on Linux. The list of tunables has all these things the one that stood out to me was this glibc mem tagging, so being able to turn memory tagging on and off, or I assume on and off, but I do see it has a max value of 255, so it's not just a boolean. But you've got these various things that can be configured at runtime using that environment value. But then in certain cases, like with SecUid IDs, you don't want to pass through all of these tunables in case they can do something that is security relevant. So they have this class of tunables that are called SXID array, saying if they have the security level, this tunnable should be removed from the list and not pass through. Which leads to the couple commits that ended up introducing this bug. Um, I guess I don't really need to go too much into the history, but they had a little bit of initially it would pass through invalid tunables, and then they tried to fix that, so they removed it and kind of processed out all of the invalid ones and all of the security ones that need to be removed. Which of course leads to some parse tunables, which I keep saying tunables, and I think it should be tunables. I'm sorry. um, yeah, that just kind of stuck in my head from something else. But you've got the string gets passed in there that's coming out of the environment variable, and they're just doing this editing inline. So in C, inline string editing, of course, there's going to be problems. And that's what we've got here in this while loop. I guess I should also mention that the tunables list in this environment will be colon separated. So you'll have name equal sign value colon name equal sign value, and just kind of repeating that for all of your tunable values. Uh, so the while true loop here is just going to iterate over everything. Looks fairly classic. While loop here that just iterate or keeps incrementing len until it finds either the equal sign, the colon, or a null byte indicating the end. Does that, then checks which character it did get. If it's a null byte, that's where it basically terminates your the tunable string, the one that's ending, adds that null byte, and then returns out from there. If it's a colon, they're like, hey, we were expecting a value, so they just kind of increment it by one and continue the loop. They go back to the beginning. But if they find the equal sign, they know the name, they start trying to track what the value is. Which again, everything here seems very normal. They're just going to increment to find the value. They're just going to increment until they find either the colon or the null byte, indicating the end. So all of that fairly normal how it's iterating through. And you can see down here where they're checking the security level of I guess they iterate all of the tunables in the list there just to check, is this one that we know about, checking the name of it and checking its level. And if it's not, then they can go ahead and write it back into the tunable string or just skip ahead on it. They, so anyway, what you're left with is this kind of edge case where at the very end here, so normally if they found if they found just the colon coming through here, so they're going through here. I'm just trying to find exactly. Oh, okay. I guess it's at the end of the loop. There's a condition I was looking for. They've got this condition that's just looking if where they're at. So after it's done, this writing of everything from that equal sign over to either the colon or the null byte. If the character that they terminated the last loop on was a null byte, it just increments the pointer basically one forward from where it was. And where P was last updated was up here when it was looking for the name. So it's just pushing it one past like the name. I think past the equal sign technically. And it's just doing that versus my apologies. I did just get that backwards. In this iterating loop, if it's not a null byte, it's going to push P forward. It's going to push this that's the tunable string, but kind of where it's currently at. So it's going to push that pointer forward past what it's just consumed because it is taking advantage of len there. Whereas if it's a null byte, this just doesn't execute at all. It never pushes it forward, but it will repeat the loop. And then it repeats the loop, and they're expecting that they're just going to land right back in here because they had a null byte. So they're just expecting to read again up to the null byte and be like, okay, now we can terminate. And they didn't want to duplicate this code down at the bottom. The problem is if you have a malformed string, which I believe they do have an example of it. I'm just not.
Yeah, they
There
have
it
like
is.
if you set a tunable to another tunable key value pair, yeah.
Yeah. So the problem is if you have two names and then the value, the way this is going to get iterated on is it's going to read the name first. So it reads up into the equal sign, which is fine. It's read the correct name, and then it's going to write, and then it's going to read to the value, which is going to be that null pointer, which, in theory appears after that last A. It's going to read that as the value. It's going to be like, okay, tunable 1 is okay. Let's write that back into the string. But because it saw the null byte at the end there, it didn't update the pointer. So you've still got that pointer that's right there at the start of tunable 2. So when this loop runs again, it's going to go ahead and run tunable 2 equals AAA. It's going to see that, so it's going to parse it once again, reading the name as tunable 2, and the value is AAA. It's going to read that again and write that into the string again. Although the string is getting that original string, it didn't reallocate anything, it didn't make it larger. So this copy is now going to be out of bounds because it's written it's written the original string back, getting you back to the original size, and then it's also writing this entire thing. Whatever values you've got there, it's writing that again, now out of bounds on that string. So fundamentally, like, to explain this really simply, well, I just walked through the whole iterator, and the problem being their attempt not to duplicate this null code by keeping it up there and letting the loop go again. The simple way of explaining this is if you give it this malformed tunable in the environment, it misreads that and ends up writing it twice. It does strip a little bit, but writing most of it twice, which is kind of a fun little issue. I'll be honest, it is something that's a little bit different than I think a lot of the string parsing issues you see, where it ends up just iterating out of bounds, being tricked into incrementing like one or going a little bit forward beyond what it should, incrementing multiple times. Fortunately, it looks like in a lot of this code, like they don't do that kind of dynamic move, like, oh, we got this character, so let's skip the next character sort of deal. They don't do that, so they don't fall into that trap. And that is another code smell to kind of be aware of. But yeah, so they end up with this buffer overflow in that string. And the way they're able to exploit this, they do talk a little bit about some potential strategies, some things that won't work. What is kind of important to note is that the allocation at this point, when it's actually allocating something, like they're actually using this minimal malloc function because at this stage, like glibc malloc has not yet been initialized. It's still very early on in the loading process. So they don't even have that started yet. And so they're just using minimal malloc, which is basically just mapping more memory as you need to as you request it. And because the mmap allocator of the kernel is kind of top down. Um,
It's
that
very
basically,
predictable, way more predictable than the heap.
yes, yeah, like you're not dealing with a lot of random data just kind of roaming around. Like this is all happening super early in the process, very predictable, just top down, just give me this data, give me this data. And one thing they do is kind of an optimization, but they've got this call example, which again, it does ultimately just end up using that minimal malloc, just looping it. Um, in that case, like they don't even initialize some of the values because fresh memory from the kernel gained super early on, they're not reusing memory, at least in their virtual address space. So this fresh memory that they've received from the kernel should already be zero super early on like this. So
Well,
they're a
mmap will just return you a zero page for new allocations. Like it shouldn't. It'll never return stale data, really. So
yeah, like nothing's been freed at this point. Like they haven't returned anything to actually have anything that's dirty.
yeah.
Um, And so basically, what their exploit ended up doing was they used their overflow, and they have a longer process here describing exactly how they came across this, but they noticed the struct link map would be reachable. And what they end up targeting is the library search path that is stored for the loader when it's going to start loading all the libraries. They overflow into that library search path, overflowing all the other values with no bytes, um, which did confuse me a little bit. I'll touch on that in just a moment, but effectively they overwrite the library search path, and that way they can get the loader to load a library that they control, like their own libc, when it gets to actually loading that. Which is kind of fun having this really early exploit. You're able to kind of target some of these really early stage events, like the loading, and like I don't think I've ever seen an exploit that's able to hijack the loading of binaries or the loading of libraries like that, which is
Well,
kind of cool to see.
they're using the memory corruption to create like an uninitialized use type scenario, which is really cool. I don't think I've really seen that before. And it's just because, you know, the assumptions that the memory is going to be zeroed is a fair assumption to make, except for in the case of memory corruption. So it's a fun subversion of what's typical. And yeah, like usually that info path would be null or would be initialized, like if it was initialized, would be initialized later on. But yeah, because you're able to do it earlier, you can kind of race it, so to speak, and get your own library loaded. So I like that aspect of it. Yeah.
Yeah, I did like that aspect. I was a little bit unclear on some of the exploitation data, so that is why I'm just kind of hand waving, getting right to the point. They targeted the link map, overwrote that value, and kind of went there because I don't understand exactly how they were able to, for example, write certain null bytes in there, because they did have to spam in null bytes, so those values, those pointers, would still get initialized by the code later, but then writing in the pointer that they wanted for that particular value. Um, it seemed a little bit unclear, but they talk about somewhere in here. The bytes are written out of bounds by parsed tunables, are also read out of bounds. I guess they do say on line 234, so let me scroll up on that.
I think we looked at it and didn't really understand what they were talking about, to be honest. I
Yeah,
think
like
we did take a look.
understanding is it's reading that environment string. So as it's writing out of bounds, it's reading the value from that original string. Maybe it's not, maybe something else is going on here, but like the way I understood it is it's reading, like you're basically getting a duplication of that original data, ends up reading it twice. Um
Yeah, I'm not totally
Actually,
sure what they mean by it.
I'm just looking here because they go value. No, okay, yeah, that should still be kind of going to the original pointer. I had a thought there, but no, that didn't work. So yeah, I'm a little bit confused on some of the details here. I want to be upfront that I am not entirely confident in my understanding of how that worked. Uh, and just kind of getting to the point with, yeah, they targeted in the library or the shared library, like loading path or search path, sorry. That's what they targeted. They managed to do it. They wrote a bunch of null bytes. Yeah, I just wanted to be clear that I'm a little bit confused on this post. I did have some trouble actually with this post in general. I don't want to spend a bunch of time like hating on it, or anything like that, because it is still an interesting vulnerability. This is more likely just there's some little connection that I'm just missing.
Yeah, there's some nuances that were hard to get because ultimately this is an advisory. Like um, it's not like a full blog post where you would expect the background information, but getting that background information was particularly difficult because even on the tunables, when I was trying to find some information on like the SXID erase behavior, it's just not documented anywhere as far as I can tell. I spent like 10 to 15 minutes trying to search on it, and I had to dig through a bit of the code to get even the littlest bit of understanding of some of the background here. So it's tricky to get a good grasp on unless you're familiar specifically with tunables and how this um like the early loading process of the GNU dynamic loader. So yeah, some of the details are a little bit fuzzy, but overall it's an understandable exploit process, and
Yeah, at its
like I
core,
said, I
like
liked how
it's
they got the uninitialized use type scenario going.
yeah, like at its core, like it's an overflow and they just corrupt data. There's a little bit of that nuance, as you said, like they're expecting to be uninitialized later on and all of that. Like there's that nuance to it, but
Mhm.
at its core, it's a fairly understandable bug.
Yeah. So, getting into another somewhat complicated bug out of GitHub Security Lab, we have a post from ManuMo on a JIT bug in Chrome. It's quite detailed as per usual with this post, so I'm going to keep it somewhat surface level, as getting into the internals of the JIT compiler and whatnot is both quite complicated and not really either of our areas. But getting into a bit of background, modern browsers leverage JIT for performance, which will basically take hot paths of JavaScript and compile it to run faster. And the JIT compiler for Chrome is called TurboFan, which will go through the bytecode of the JavaScript function that's hot pathed. And by hot path, I just mean it's being called and executed a lot. And it will transform it into nodes, which will then go through some optimization passes to see which nodes don't have some important impact or effect on the dependency and can be dropped. And the information on the state of objects that are being used, such as the offsets of fields and whatnot, because obviously JavaScript objects can get quite complicated. They have to track that in a mapping. And whenever an object is accessed, say like a parameter to a function or something, and accessing a field on that object, the compiler will speculate on the layout using the map of the object to perform optimization and whatnot. But dealing with that is extremely hard because you have a lot of operations in JavaScript that can internally taint the state of the object, and you have to keep track of that as a JIT compiler. For example, a callback might be invoked that switches out the object type after reading some property from it and then changing that property after the callback. The JIT compiler has to keep track of all these things. And this problem was made even harder and even worse with the feature that landed in Chrome 95 called concurrent compilation, which is where Turbofan can JIT functions in a background thread while the main thread is running the code like as normal in the interpreter. So of course, this introduces the possibility for races to pop up. For example, what happens if the compilation process changes an object while the interpreter is executing it in the main thread? So that's kind of where this bug comes into play. Not exactly, it's not quite a race condition. The function that's particularly responsible here is this prepare install function of the compilation dependency class. Which we'll call this ensure has initial map function, which what exactly that does isn't super important. What is important is that it can implicitly change the layout or map of an object because it'll run some optimization on it. Now, this prepare install function is actually called on the main thread, not on the background JIT thread, which makes it seem like, hey, okay, it won't cause any concurrency issues with the main thread because it's running off the main thread. But the problem is sort of how the main thread is scheduled, so to speak. Because if you have a function that accesses fields in a loop, for example, that loop can be interrupted to call this prepare install to change the mapping. So, say you access some field in that function before the loop, run the loop a while, and then it gets interrupted. That prepare install method is called. If you then access that field again after the loop, it's possible that layout changed and there's no additional checks that are inserted after the loop. So it will end up accessing at an incorrect offset. And that basically leads to a sort of type confusion scenario, which in browsers is game over. Basically, he goes through the process of exploiting the bug, which I won't go into too much, as it involves a lot of browser internals. But basically, they use that offset confusion to smash a named dictionary's capacity to get an out of bounds access, and then use the out of bounds access to create a more powerful type confusion between objects and arrays, to get your more typical fake obj and leak obj type primitives. If you're curious on more on what I mean there, you can check out the Frack paper by Salo on attacking modern JavaScript engines. But yeah, the whole idea here is that you're able to get this confusion between the offsets because the optimization will change the mapping of the object, and then you can spiral that into a more useful corruption to RCE, the Chrome renderer. So quite a cool post. There is a fair amount of detail that I skipped over there. Like I said, if you're not uh, that familiar with like the Chrome internals, then a lot of the objects and methods that are being mentioned here won't really mean anything to you. So that's kind of why I skipped over some of them. But uh, it's kind of your standard optimization type bug in the JIT compiler. And like I said, it was these types of bugs were exacerbated by the concurrent compilation feature, which is very interesting. I'm surprised they would ship something like that. I guess there must be some performance need for it, but it sounds like bugs waiting to happen. So I wouldn't be surprised if we see some more coming out of the concurrent compilation feature edition.
Yeah, it's kind of a surprising feature because it definitely adds a high degree, or it seems like it would add a high degree of complexity. Uh,
On something that's already super complex.
yeah,
Yeah.
yes, very much already complex. Yeah, adds a high degree of complexity there. Although I could imagine there is a pretty substantial performance benefit to being able to do the compilation, in
In
the
the
background
background.
thread and all of that. Like
Yeah.
it does make sense, but definitely from a security standpoint, like it is adding uh or is probably I haven't looked at the code, but it is probably adding quite a bit of complexity in there. It, it is kind of interesting, like the use of the interrupt as a way of kind of, like I said, it's not quite a race condition, but you kind of get a similar vibe from it.
It's like an
Of like,
interleaving race condition, sort of.
yeah, I guess. I was going to say maybe like I could relate to like reentry, or it's coming
Sorry,
back into
that's
that
what I was
code.
looking for. The term I was looking for was reentrant. Yeah.
Yeah. Yeah, it kind of goes with that, which haven't seen a lot of bugs like that, but definitely interesting to see. And definitely, that sort of thing could happen elsewhere. Obviously, not this exact case where, it's a JIT thing, but there are these complexities when it comes to having multiple processes or multiple threads going on that always just seems surprising.
Yeah. So that's most of the topics we have for this episode. We do have one shout out that was that's a post that was put out by Synactive, which talks about Scudo, which is an LLVM hardened allocator that I believe Android is using as of Android 13. Um,
Android 11, it's been the default in user line for a while.
oh, sorry, yeah, Android 11. So yeah, the device they were testing was Android 13. That's where I got the numbers mixed up. But yeah, the post goes into some background. They do like an in-depth assessment of the allocator, what it does, talking about how the heap is managed internally, talking about the headers of the chunks for allocating from the heap, and the security implications of that, making things like overflows a little bit harder and whatnot. So it's more of a deep dive on the allocator internals, which is why we left it as a shout out. There is a bit of a section towards the end that talks about the security implications, which are somewhat interesting. I mean, it's not an end all be all as you would expect. uh Various scenarios like use after free and um well, yeah, primarily like use after free and type confusion, it won't entirely prevent, and it can be gotten around, especially if you have a good set of primitives to work with. But it is a hardened allocator. It does add complication to exploit development, and it can kill certain scenarios, I'm sure. So yeah, Synactive did a pretty good deep dive here. It's worth the read, especially if you're interested in allocator internals. So just wanted to give it a quick shout out.
Yeah, definitely worth the read, and has a lot of that background information if you are going to try and do something on Android or somewhere else that this is used. I can't think of anywhere I've actually seen it used outside of Android, but I have to imagine it is used outside of there. Um, and yeah, the ultimate conclusion of it is like a lot of the defenses can be circumvented, but there is a steep cost to doing so for the attacker in terms of like the primitives you need to have. So not impossible, but a lot, and actually a lot of the primitives aren't that uncommon either. They're more primitives though that you would think of when you're actually trying to attack the allocator itself, the type of primitives you would need for like the various house of attacks against the glibc allocator. Um Kind of things like that you would need here, like the ability to allocate and retain them and release at the right moment. They're not unheard of attacks, and actually, especially retaining and releasing, that is common with use after free too. Um, and of course, strength. Like they're not unheard of primitives, but it does raise the bar. It does mean you need to do a little or a good chunk more work to exploit some of these issues because of the allocator now.
All right. So, as always, thanks goes out to everyone who tuned in. If you want to go back and check out past episodes, you can find the most recent ones on Twitch and all of them on YouTube, Spotify, Apple Podcasts, and more links off Anchor. Feel free to join our Discord and follow us on Twitter. Links for those are down below in the description. And once again, next week's episodes will likely be canceled, and check out our Discord announcements channel for updates and whatnot on that. And we'll catch you next time.